So what am I going to be doing today? I'm going to start talking about like connections, like what you guys saw in like the previous lectures. And then I'm going to just talk about briefly about like single loop analysis. Basically, I'm going to talk about like KVL and KCL one more time, and we're going to do like a few examples. And then in the next lecture, we're going to start doing a bit like more examples and talk about like other types of like connections, basically delta Y connections. But that's the plan. All right. As you guys know, there are two types of like very important elements in a circuit. When we're talking about elements in a circuit, we're basically talking about like passive elements, the ones that cannot generate energy, right? For example, resistors, capacitors, inductors, and all those things. And we also talk about like active elements, which basically means we're talking about like sources, right? So let me quickly write it down. Elements in the circuit. Great. We have passive elements. For example, resistors, capacitors, inductors. And we have active elements. Basically as our sources. And as we discussed before, we have two types of like sources. We have dependent sources and we have independent sources. Independent sources are the sources that their value has nothing to do with anything else in the circuit. The value can be time varying. The value can be basically like DC. But what's important here is that that value does not depend on anything else in the circuit. Okay? So we have types of sources. The first type is independent sources, which means their value does not is this my mic or let me turn it off really quick. Anyways. So back to this guy. Independent sources, their value does not depend on anything else in the circuit. We have two types of independent sources. We have voltage sources, which we show them with this circle thingy, but like plus and negative. Let's just say its value is 5 volts. So this is a voltage source. It's an independent voltage source. And it's an independent current source. Again, its value can change with time or can be like something constant, but it does not have anything to do with anything else in the circuit. Let's just say its value is like 4 sine 2t plus 4. As you can see, it changes with time, but it's got nothing to do with anything else in the circuit. The second type is dependent sources. Dependent sources are the sources that their value depends on something else in the circuit. And depending on what it depends on and what type of like source we have 4 types of like dependent sources. So we have 4 types of dependent sources. The very first type is dependent voltage source. It's a dependent voltage source that its value is being controlled by a voltage in a circuit, right? So we have a dependent voltage source that its value being controlled by something, by another voltage in the circuit. So I have a source this is my dependent source, right? Its value is some constant, let's call it Gm, times another voltage. And this voltage, let's just say this is the rest of my circuit. And from this point to this point, that's Vg. Right? So for example, if I have like a circuit that looks like this, Vg could be this guy. Right? So it basically depends on voltage in a circuit. Right? Another type is the dependent voltage source. But this time its value is being controlled by a current in the circuit. Right? That its value being controlled by another current in the circuit. What's important here is that even though the value is being controlled by the current, it is still a voltage source. And we're treating it as like a voltage source. Right? So let's just say this is my voltage source. Right? And it depends on like some new m, for example, Im. And this Im is some current in the circuit. So if I want to go back here, my example, this is Vm, new m, Im, and let's just say this is Im. So the value here depends on this current, right? It could be anything, right? It could be any current in the circuit. This is just an example. The third type is the dependent current source that its value depends on another voltage in the circuit. Right? I still have like a current source, but this time its value is being controlled by some other voltage in the circuit. So if I have, let's just say, this guy, let's just call it Rm Vm. And this is the rest of my circuit. There is some voltage in the rest of my circuit, and the value of this current source depends on that. So if I have, for example, this, again, voltage across this could be V. Okay? Again, just remember, this is just an example. Right? And lastly, I have like another dependent current source that's value is being controlled by another current. Right? So I have a dependent current source that its value is being controlled by another current in the circuit. Right? So I have basically this guy. Let's just say it's gamma m Im. And this is the rest of my circuit. And there is a portion of the circuit that has the current Im. Right? So if I have, for example, this circuit, that's gamma m Im. And let's just say, for example, current through here is Im. So we have 4 types of dependent sources. Again, what we're doing, we're basically treating them the same as like a source, right? But what differentiates these type of like sources from independent sources is the fact that their values are being controlled by something else in the circuit. And unlike independent sources, that their value is something that's given to us, it's 5, 6, 10, whatever, or it's changing with like time, and it has nothing to do with the rest of the circuit. These sources, if you look at the values are basically dependent on something else in the circuit, and hence the name, right? Any question? Is that clear what's happening here? Yes? Now we got it out of the way. Let's go back to our like passive elements. The very, very first passive element that we're dealing with is just a resistor. Okay? So we have a resistor. As you guys know, like a resistor is like an element in the circuit that impedes the current from flowing through the wire, right? We usually show like a resistance with this guy. Let's just say the value of this resistance is R, current through it is I, and voltage across it is V. We know there is a relationship between this V, I, and R. And this relationship is called Ohm's law, right? So we know V equals Ri, and we call this Ohm's law. And obviously, if I know the relationship between V and I definitely know the relationship between I and V, right? So if I basically pull this one down here, I know I equals V over R, right? And that's like another way of representing Ohm's law, right? But here's a very important thing. Oftentimes when we're looking at circuits, we see more than one resistor, right? So we got to somehow like simplify it down to something that's easier for us to like analyze, handle, right? And depending on like how these resistors are connected in the circuit, we have 3 types of like connections. We have series connection, we have parallel connection, and we have neither of them. We're going to talk about like series and parallel today. For the neither, oftentimes we cannot do anything, but there are like some special cases. Like for example, if the way that like these like resistors are connected to each other, it looks like a delta, or if it looks like a Y, then there are like ways that we can simplify it. But in general, we cannot do much. We have to like learn like other methods to solve the circuit. But as soon as like we see, you know, series or like parallel, we know exactly like what to do. So let's talk about them. Let's just see like what they actually mean, right? So connections. The first type is series. We call 2 resistors connected in series when, first of all, they're back to back. Basically, what it means is that like the head of like one of them is the tail of like the other one. Second condition is that current through one of the resistors should go completely to the second resistor. So there is no leakage in here, right? So let's just write it down. We say R1 and R2 are in series if and only if these 2 conditions hold. First, they're back to back. Second, current through R1 is exactly the same as current through R2. Right? That's the definition. So let's just call like this point over here A, this point over here B. Let's just call the entire current here I. While current through this guy, let's just call it I of R1. This one over here, I of R2. Let's just call voltage across this resistance V of R1. Voltage across this guy, V of R2. Right? Let's see what we know. First of all, looking at this graph, this picture that I got over here, R1 and R2, they're in series. Why? Because they're like back to back. Whatever current I have through R1 is going through R2, and there is no leakage. Right? So what do we know? We know I through R1 is exactly the same as I through R2. We're lazy. I don't want to keep writing R1 and R2. Let's just call it I. Right? And this I is exactly like whatever that's going through like the circuit from point A. Right? What can we say about voltage across R1 and R2? Are they the same? Yes? No? Absolutely not. Under very special circumstance, yes. If R1 and R2 are exactly the same, like in terms of like values, then I through R1 is the same as I through R2. And V across R1 is the same as V across R2. But that's not the case all the time. It is the case all the time that current through one is the same as current through the other one. But voltage across these two can be different. So V across R1 is not the same as V across R2. Right? So that's pretty nice. But sometimes we want to like simplify. So we want to replace whatever I have between point A and B replaced by only one resistor. It turns out if I have like the resistors back to back, I can replace it by one resistor, and the value of that resistance is the summation of these two resistors. So if I look at point A and B, I can replace that resistance, but by R equivalent. And it turns out this R equivalent is R1 plus R2. Right? Let's understand this a little better. Remember, this is equivalent. And by that, we mean everything about like this, every outside thing about this should be the same as whatever I have on the top. Right? Basically, if I look at from point A and B, these two things should be exactly the same. Right? So what can I say about current through this R equivalent? Can we say something about it? Can we? It's exactly the same as current through R1, and it's exactly the same as current through R2. Why? Because they're back to back. And whatever current that's flowing through one of them, it should flow through another one. And on top of that, if I look at point A, I know the current through that is I, which is exactly the same as I of R1 and I of R2. So I, let's just call that I equivalent, is the same as I of R1, is the same as I of R2, is the same as I. Right? What can we say about voltage across this R equivalent? Well, remember, this is supposed to be equivalent to the top. So whatever I see from point A to B should be exactly the same. What is the voltage across R1 and R2 then? It's voltage across R1 plus voltage across R2. Therefore, if I want to have something equivalent, if I look at it from A to B, voltage equivalent should be V across R1 plus V across R2. So V equivalent is V across R1 plus V across R2. What else can we say about this? Well, we can say we can generalize this. We can generalize this to any number, any finite number of like resistors, right? So let's just say I have generalization. Let's just say I have n of them. This is point A, this is point B. I can replace the whole thing from point A to point B by one resistance, and we call that R equivalent. And we know that R equivalent is the summation of all these. Again, exactly like what we have over here, right? So we can replace this by a circuit from AB. This is R equivalent, and R equivalent here is R1 all the way to R. Again, remember, this is exactly like this special case with like two resistors. So we know if I want to like have like current through R1, that's exactly the same as current through R2 and all the way to Rn. We know voltage across R1 is not the same as voltage across R2, and so on and so forth, right? And we also know if I replace like the whole thing, the whole circuit, with like n resistors, with only one, which is my equivalent, current through this equivalent is exactly the same as current through R1, exactly the same as current through R2, and so on. Right? Is that clear to everybody? All right. Let's move on to like another connection, which is parallel connection. What would we say two resistors? Let me just call them R1 and R2. Let's just call this point A, point B. This is I. This is I of R1. This is I of R2. Let's just call voltage across this V of R1, voltage across this V of R2. Right? We call these two resistors connected in parallel if one, they're sharing the same head and tail. So if I look at this, this is the head of this guy, this is the head of this guy, so they exactly have like the same head. If I look at the tail of this guy, they're exactly the same. So one, they share the exact same head and tail. Second, if I look at voltage across R1, voltage across R1 is exactly the same as voltage across R2. So the second condition is voltage across them are exactly the same. Right? So if I write it down, what do I know? I know V across R1 is exactly the same as V across R2. Right? So V across R1 is exactly the same as V across R2. Well, let's just call it V. Right? How about current through R1 and R2? Are they the same? Absolutely not. Again, in the very special like case where R1 and R2 are exactly the same, then sure, like whatever I have going through that junction, it splits equally. But in general, I through R1 is not the same as I through R2. So I through R1 is not the same as I through R2. Right? And as a matter of fact, if I look at it, if I look at point A, the current that's going into that junction is I. So that I equals whatever current that's going through the top resistance plus whatever current that's going through the down resistance. Right? So if I have I is exactly I of R1 plus I of R2. Right? Similar to series case, we can replace like this connection with only one resistance. Right? Let's just call it like point A, point B. And this is the equivalent resistance. This time, however, to find this equivalent resistance, it's not as simple as the series case. It turns out if I want to compute this R equivalent, I have to use this formula. 1 over R equivalent is 1 over R1 plus 1 over R2. Right? This case is like very, very important. Let's work it out a little more. Let's just simplify it down a little further. So the way I can do this, I can basically find like the common denominator here, right? I can basically say this is R2 plus R1 divided by R1, R2. And that's basically 1 over R equivalent. I didn't do much, right? I just found the common denominator, and that's it, right? From here, I know R equivalent is R1, R2 divided by R1 plus R2, right? So I can either use this formula, or I can use this. They're exactly the same, right? But since like two resistors, usually like it's very like common and we see it a lot, we're going to simplify it so we know exactly like how we can compute it, right? What else do we know? What can we say about like V equivalent? Basically voltage across the sky. What can we say about it? Remember, V equivalent is the same as voltage between A and B, right? So if I go up there, what is voltage between A and B? It's V across R1 or V across R2. But they're exactly the same. So what can I say about this V equivalent? What can I say? It's V across R1 or V across R2, or as we called it up there, it's V. Right? How about I equivalent? Remember, I equivalent is this I. What is it? That's basically the I that's coming out of point A. What is it up there? That's I, right? And since this is supposed to be exactly the same as the one on the top, then I equivalent must be I, right? But we already know this I is I of R1 plus I of R2. So I can write this as I of R1 plus I of R2. Right? Just like series, we can extend this. We can generalize it to like n resistors in parallel. So let's just have the generalization. Let's just say I have n of them. Right? I can replace this by 1 R equivalent. And this R equivalent is computed using this one. Right? Again, whatever we said over here holds true over here. Voltage across R1 is the same as voltage across R2 all the way to voltage across Rn. And again, that's exactly the same as voltage across this R equivalent. Right? To sum up like what we talked about, if we have a bunch of like resistors in series, what we're adding up is resistors, right? However, if we have like a bunch of like resistors in parallel, what are we adding? There is a name for it. We talked about it. Conductances. 1 over R is called conductance. So we're basically adding up all the G's. So we call it 1 over RG, right? So that's all about it. That's it. Any question? Is that clear to everybody? So these are very, very important things. They seem like very easy, but they're basically like the fundamental things that we should know and we should always use. So let's just make sure that we know exactly how they work. Is that clear to everybody? Nice. So far, we have a bunch of tools. If you have like series connection, we could simplify it down to like 1 resistance. If I have parallel connection, I can simplify it down to like 1. And then I know Ohm's law, right? But that's not enough. Like whenever I'm like looking at the circuit, I got to be able to like have like more tools to analyze the circuit. My circuit does not always consist of like one element, right? There's actually no circuit with one element. It's just pointless, right? So I gotta have like some more tools to be able to like analyze the circuit. There are two very, very powerful laws that we can use in any circuit. And those are called Kirchhoff's laws. We have two types of like Kirchhoff's law, current and voltage. Let's see like what they say. Let's start by Kirchhoff's current law. What does it say? What it basically says is, if I look at any node in a circuit, any node, whatever current that's going in should be the exact same as the amount of current that's going out. Okay? So current going in is the same as current going out. In other words, I can assign some basically sign to like my current and say the algebraic sum of like my current should be 0. What it basically means is that like take one of these things to the other side, right? So this is equivalent of saying algebraic sum of all currents should be 0. But as soon as we're talking about like algebraic sum, what we mean is that like there should be some sign, right? So let's just have like a convention. Let's just have something for us, right? Let's just say if I have a node and the current is entering into the node, then let's consider that current to be positive. If we're exiting a node, let's think of it as like negative. Again, this is our convention. It could be all the way around. It does not matter. In a second, I'm going to show you why it doesn't matter. But we're going to stick to this. Okay? So let's just say I have this node here, right? I have like this current going in, this one going in, and this one going out. The first interpretation tells me whatever goes in should come out. Well, I1 and I2 are going in. I3 is going out. So that's the first interpretation. Second interpretation is that if it goes in, let's think of it as positive. If it comes out, let's think of it as negative. I1 and I2, they're going in, so they're positive. I3 is going out, so it's negative. And it should add up to 0. If you compare the second equation to the first equation, they're exactly the same, right? If I assumed reverse, if I exit a node, it's positive. If enter a node, it is basically negative. What would have happened? Basically, I had this equation, everything multiplied by -1, right? But since it all adds up to 0, multiplying by -1 does not change anything, right? So that convention is good enough. So we're going to stick to that, right? Or we're going to just like go with whatever comes in should be the same as like whatever comes in. How about KVL? What KVL says is that if I look at any closed loop in my circuit, if I go around it and I add up all the voltages that I have, it should add up to 0, right? So in any closed loop, algebraic sum of voltages should be 0. Again, we talked about algebraic sum. It means that there should be some sign. So let's just have our convention. Again, does not really matter. We're going to stick to this convention. If we're looping around, and if we hit like the positive sign, let's just say that voltage is positive. If we're hitting the negative sign, we're going to think of it as like a negative voltage. So encountering positive, it means it's a positive voltage. Encountering negative, it means it's a negative voltage. Let me just like give you like a quick picture. Let's just say this is V1. Let's just say this is negative, this is positive, this is V2, and this is V3. Right? So what this law tells me is that if I loop around and I add up all the voltages, that should be 0. So I'm going to start from here, and I go clockwise. Right? So I have plus V1 minus V2, because I hit the negative sign over here. And then over here, I hit the positive sign, so it's plus V3. And according to this law, that should be 0. One question that you should be asking is that, why did you choose clockwise? Why not counterclockwise? Let's see what happens. Let's just choose counterclockwise. Let's just go this side. So let's start here. What do we have? We have negative V1, negative V3, plus V2, and that should be 0. Are these any different? Absolutely not. I just need to like multiply the bottom equation by -1. I get exactly the same equation. So the fact that I want to go clockwise or counterclockwise, it's completely up to me, whichever direction I want. As long as I stick to this. As long as I hit like a positive sign, I think of it as positive. Hit a negative sign, I think of it as negative. It does not matter like what direction I choose, because it's just a matter of like a sign. It's a -1, as you can see over here. And since it adds up to 0, if I multiply everything, like both sides by -1, nothing would happen. Right? Any question? Any question? Is that clear? This is by far one of the most important laws that you learn in this class. And if you're an electrical engineering major, you're going to take like 334 and 335. Even in those courses, these two are the most important laws that you're going to use. We're good here? Everybody knows what's happening here? Yes? All right, let's do a few examples. Example 1. Let's just say I have a circuit that looks like this. This is Vs, this is R1, this is R2. And let's just assume we know Vs, R1, and R2. Right? And the question is asking me, find this I, and find voltage across R1, and voltage across R2. Right? We have a single loop here. Our instinct is, let's use KVL. So let's just assume I have this direction, and I'm going to write a KVL for that direction. What do I have? Let's just start here. I have V of R1 plus V of R2 minus V of S equals 0. But I'm going to take like V of S to the other side. So I'm going to write it as equals to V of S. Right? We know that. What is V across R1 though? What is it? We know how to compute it, right? So if I have like a resistance, what is V across this? V is Ri. Right? So what is V of R1 then? It's R1 times I, right? So it's R1 times I plus, what is V across R2? It's R2 times the exact same I, because they're in series. So it's R2 times I, that equals Vs. So I can simply find I, right? I can factor out this I, and that's Vs. Therefore, I is Vs divided by R1 plus R2, right? Again, I chose the hard way to find this I. Why? Because I know like R1 and R2, they're in series, they're back to back. I could just combine them, right? I just replace it by the equivalent, which is like R1 plus R2. And then I know exactly like what voltage across it is like Vs. So I could use Ohm's law, right? But I specifically use this because I just wanted to show you KVL, right? But you could just like replace it by the equivalent. Now I have this I. What is V of R1? Well, it's just R1 times I, right? But I already know I. I is right here. I can plug it in here. So I have R1 divided by R1 plus R2 times Vs, right? I can do the same for R2. That's R2 times I. Therefore, it's going to be R2 divided by R1 plus R2 times Vs. Let's look at this a little more. One thing that you notice immediately is that if I want to find voltage across R1, the value of this voltage depends on the value of R1. It directly depends on the value of R1, right? So if I have V of R1, it depends on this R1. And the same thing for R2. The value of voltage across R2 depends on R2, right? Another thing that you could notice is that if I have that voltage source Vs, that Vs is split between voltage across R1 and voltage across R2, right? So it's divided between like these two resistors. And hence the name of like this circuit. This is called voltage divider circuit, because it basically divides the voltage. You can check that Vs is indeed VR1 plus VR2. You can check this. This is by far one of the most important circuits in this class. Why? Let's just imagine like this scenario that I wanted to like, I have like a very like complicated circuit, right? If I could simplify down the circuit to something like this, then I know everything about it. The question is, can I? It turns out, yes, we can. And that's called like the Thevenin equivalent of a circuit. We're going to get to it in a little bit. But for now, we just know this is a very important circuit. And this is basically how it works, right? Let's go back to like very hard example that we have. Like, let's just say we have like a very complicated circuit. We were able to like simplify down to like a circuit like this, right? And let's just say in the very, very complicated circuit that we have, we change the value of R2 in there. If I wanted to solve that very complicated circuit, I have to like start from scratch, right? Which is hard. Oftentimes it's pretty hard if I have like multiple loops and like multiple like nodes. It's always pretty hard. But if I have like this circuit, I can stick that R2 in this circuit, right? And I know everything about it. Solving this circuit is very, very easy. We know everything about it, right? We're going to learn how to convert any circuit into a circuit that looks like this. And that's called Thevenin equivalent. We're going to talk about it later. Another important thing about this is that like I can generalize this to any number of resistors I want, right? And I know if I want to like find voltage across, for example, like the ith resistance, voltage across that ith resistance is proportional to the value of that ith resistance divided by the whole thing times Vs. Right? So we can do that. Any question? Is that clear to everybody? All right, let's do another very important circuit. Let's just say I have a circuit that looks like this. Now let's just say I know R1, R2, and I of S. And the question is, what is I through R1 and I through R2? Right? I need to find those. Right? What can we do? Let's write down our observations. Very, very first observation is that R1 and R2 are in parallel. Right? What does that tell me? It tells me voltage across R1 is exactly the same as voltage across R2. Right? That was our definition. So let's just write it down. Our first observation is V across R1 is the same as V across R2. Well, let's just call it V. Right? We can do that. What else can we see? We can see if I write a KCL at this point, at this node, what do I get? If I write the KCL at this point, I know whatever current that's coming out should be the exact same as whatever current that's going in. What is it that's going in? I of S. The things that are going out, I of R1 and I of R2. Right? So I know, writing the KCL, IS equals I of R1 plus I of R2. Right? We know that. What else do we know? We also know if I have a resistance, let's just say current through it is I, voltage across it is V. I is V over R. We know this, right? That's Ohm's law. So let's use this fact, I equals V over R, and apply it in my KCL. I can do that, right? Well, IS is IS. What is I of R1? It's V across R1 divided by R1. But what is V across R1? That's this common V, right? So it's V over R1 plus the same thing over here, right? It's V over R2. Right? I can factor out this V, simplify it, and basically find what V is. Let's do this. So I have 1 over R1 plus 1 over R2. So it's V. Again, find the common denominator. So that's it. Now I can find V, and I know V is R1 times R2 divided by R1 plus R2 times IS. Right? This is times. Just put it this way. Right? I didn't do much. It's just like I find the common denominator and then invert it. Right? Because I wanted to find V. Now I have V. I know exactly like what I of R1 is. What is it? It's V divided by R1. But I already know V. V is this guy. I have to divide this thing by R1. What happens if I do that? Well, R1 and R1 cancel. So what I get is R2 divided by R1 plus R2 times IS. So it's going to be R2 divided by R1 plus R2 times IS. I can do the same thing for R2. So it's V over R2, which is R1 divided by R1 plus R2 times IS. Right? And as you can see, current through R1 is proportional to R2, and current through R2 is proportional to R1. And it should make sense to us intuitively. Why? Because if R1 is bigger than R2, we're expecting to have less current going through R1. than R2. Right? And again, you can verify that I of S is I of R1 plus I of R2, and hence the name that's called current divider circuit. Okay? This is again a very important circuit, right? Because we're going to learn how to simplify down any very complicated circuit into this, and we call it Norton equivalent circuit. Right? One important thing is that we cannot generalize this. We can, but it gets like super messy. So instead, if we have like more than like 2 resistors, we can always use, parallel connections and simplify it down to like these 2 resistors, and then solve it from here. What we're going to be doing next lecture, we're going to do a few more examples on these things and basically like the applications of KVL and KCL. Any question? All right, I'll see you guys Friday.